Ever looked up at a satellite, one of those bright dots moving across the night sky, and wondered, how does that thing actually know where it's pointing?
Yeah, it's not like there's someone up there with a map and compass, right?
Exactly. I mean, no tiny astronaut fiddling with a joystick. So this time we're taking a deep dive into satellite attitude dynamics.
Which is basically the physics of how satellites stay oriented, how they rotate and point where they need to.
We're using Spaceflight Dynamics by Craig A. Kluever as our main guide here.
A solid resource.
And our mission today really is to give everyone a clear understanding of the basic ideas, the invisible forces and clever engineering behind it all.
Without getting bogged down in like super heavy math, we want you to get the concepts.
Okay, let's get into it then.
So, what's fascinating and maybe not immediately obvious is just how critical this orientation, this attitude is. We often focus on the orbit, the path,
Right, where it's going.
but how it's pointing. That can make or break the entire mission. Think about a weather satellite. If its camera isn't pointing down at Earth, but say out into deep space, well, your morning forecast isn't going to be very useful, is it?
Huh, no, definitely not. Or like those communication satellites.
Exactly. Their antennae need precise aiming to beam signals correctly. So when we talk attitude, we mean its angular orientation relative to some reference frame.
Like Earth or the sun or the stars.
Could be any of those, yeah. It's not just about the static pictures in the book, figure A points this way, figure B points that way. Imagine the real world consequences if it gets it wrong.
Totally. Getting it up there is only like half the job.
Mm-hmm.
Knowing which way is up for the satellite is key.
Mm-hmm.
Now, understanding this rotation business, it seems to start with something called rigid body dynamics. Sounds a bit intimidating.
It sounds more complex than it is, maybe. Rigid body just means we're treating the satellite like a single, solid object. Its shape, how its mass is spread out, that stuff doesn't change.
So it's not like a wet noodle flopping around in space.
Precisely. It keeps its shape. And this lets us split its motion into two bits. First, there's how its center of mass moves through space.
Okay, the overall movement.
Translation.
That's translation, yeah.
Mm.
But what we're digging into today, the core of attitude dynamics, is the rotation around that center of mass.
Ah, okay. Like a spinning top rotating around its central point.
That's a great analogy. And to describe how fast it's spinning and in what direction, we use angular velocity, usually written as omega.
The way its orientation is changing. Got it.
Right. And this naturally leads us to two really important ideas, angular momentum and torque.
Okay.
Angular momentum, often labeled h, is basically, think of it as the amount of rotational oomph a body has, its tendency to keep spinning.
Like inertia, but for rotation.
Sort of, yeah. It depends on two things. That inertia, you mentioned how resistant it is to changes in rotation and its angular velocity, how fast it is spinning. The relationship is h equals I times dρ, where I is the inertia matrix, which sounds complicated, but it just describes how the mass is distributed. Okay, like whether it's a sphere or a long rod or something weirdly shaped.
Exactly. And that angular velocity. Now, crucially, this inertia matrix I is constant if we look at it from the satellite's own perspective.
The body fixed frame, you mean? The camera strapped to the satellite idea.
That's the one. Now, if we want to change that angular momentum, speed up the spin, slow it down, change the axis it's spinning around, we need
A twist. A push.
a torque or a moment. We usually call it M. Torque is the rotational equivalent of force.
Makes sense.
And the fundamental rule is an external torque, M, causes a change in angular momentum, H, over time. So M equals the rate of change of H.
Gotcha. Torques make things twist. Now, you mentioned perspective.
Yeah.
Frames of reference. This inertial frame versus body fixed frame thing seems important.
It really is, because how we describe the change in angular momentum looks different depending on our viewpoint.
How so?
Well, in an inertial frame, imagine that fixed camera watching everything. The rate of change of H is just, well, the rate of change of h, but from the body fixed frame.
The camera strapped to the spinning satellite.
Right. Because that frame is itself rotating, the change we see, h by 10 up to 50 brands 0, isn't the full picture seen from outside. There's an extra term.
All right.
It's related to the frame's own rotation. The full inertial change, h by v 10 x by 50 v 0 back v 20 by 820 by 90 euro, is the change seen in the body frame plus this extra rotational term O cross h.
Whoa, okay, so the rotation of your reference point changes how you measure the change in rotation. That's a bit mind-bending, like that fly on the spinning record player example.
It is a bit, but it's crucial for getting the equations right. And these equations, the ones that tie everything together, are Euler's moment equations.
Big ones.
They are the core equations for rotation. They relate the external torques acting along special body-fixed axes.
The principal axis.
Exactly, the principal axis, kind of the natural balance axis of the satellite. They relate the torques along those axes to how the angular velocity components are changing, and also involve the satellite's moments of inertia about those same axes, I euro and I.
So these equations tell you how torques make the satellite spin change, taking into account how its mass is distributed along these special axes.
You got it. Using principal axis just makes the mass tidier because the inertia matrix becomes simpler, just those three values on the diagonal.
Okay, Euler's equations. The laws of satellite spin. Now let's imagine, what if there are no external torques? M equals 0. Our satellite is just out there drifting. Does it just stop rotating?
Good question. No, not necessarily. If m is 0, the total angular momentum h stays constant. Constant magnitude, constant direction, as seen from that inertial frame.
So it keeps spinning.
It keeps its rotational state.
What?
Think about giving a bowling ball a spin as you let it go. No more forces or torques from your hand, but it keeps spinning down the lane, right?
Yeah.
The simplest case is if it's already spinning perfectly around one of those principal axes. We call that pure spin.
Nice and stable.
Very stable, especially if it's the axis with the largest moment of inertia. The angular velocity and angular momentum h vectors line up perfectly. It just spins smoothly, like a perfectly thrown spiral football.
Love that analogy. But what if the spin isn't perfect? What if it's slightly off axis, like my football throws usually are?
Yeah.
A bit wobbly.
Yes. Well, that wobbly football is exactly the right mental image. If the initial spin isn't perfectly aligned with the principal axis, you get this more complex motion, often called coning or wobbling.
Coning.
Yeah. The satellite's angular velocity vector starts tracing out a cone shape around the principal axis it's closest to, typically the one with the biggest or smallest inertia. We call that cone fixed in the satellite's body, the body cone. But wait, there's more.
Oh boy.
Simultaneously, that same vector is also tracing out another cone, the space cone, this one fixed in inertial space around the constant angular momentum vector h.
Whoa, so it's like one cone rolling on another cone?
Right. That's a fantastic way to visualize it. The body cone rolls without slipping on the space cone, and the line where they touch is the instantaneous angular velocity vector.
Okay, that's intricate. This wobble, is there a way to measure it?
Yep, we use the nutation angle. Theta, that's the angle between the angular velocity vector and the principal axis the body cone is centered on. And we also talk about the rates of change of the orientation angles, precession, and spin rates.
So even with nothing pushing on it, a satellite can do this complex little dance all by itself.
Pretty much. And it's not just theoretical. You mentioned the Stardust sample return capsule.
Yeah, the one that spun during re-entry.
Exactly. That's a perfect real-world case. They spun it up, I think, around 13.5 RPM, specifically for stability during that fiery plunge back to Earth.
Makes sense.
But even with careful engineering, the spin wasn't perfectly aligned with its main axis. There was a tiny tilt, maybe 1.5 degrees, between the intended spin axis and the actual angular velocity vector.
And that caused this wobble.
It caused nutation, yes. Knowing its moments of inertia, too, were equal, I about 1.8 kilogram-associators, and the main spin axis I was larger, 2.45 kilogram-associators, allowed engineers to predict and analyze that wobble, calculate the precession rate, and ensure it wouldn't destabilize the capsule. It shows how these torque-free principles applied directly.
Wow. Okay, so sometimes you want the spin, maybe even a little wobble is okay if you understand it. But space isn't perfectly empty, is it? Things do push on satellites.
Absolutely right. Torque-free motion is the ideal baseline, but the reality is satellites are constantly subject to external torques, little nudges and twists.
Okay, so what kind of things are we talking about?
Kluever's book highlights three main culprits: aerodynamic torque, solar radiation pressure torque, and gravity gradient torque.
Aerodynamic torque. But satellites are way up high. Isn't the air super thin?
It is very thin, but it's not a perfect vacuum. There are still some air molecules up there, especially in lower Earth orbits. And if the satellite hits these molecules,
There's drag.
there's drag. And if the effective point where this drag acts the center of pressure isn't exactly lined up with the satellite's center of mass.
Ah, it creates a twisting force.
Yeah.
A torque, like a badly designed weather vane.
Exactly. The strength depends on things like atmospheric density, the satellite speed, its size and shape, its drag coefficient. But the tricky part, as the book notes, is that density changes a lot.
Like with solar flares and stuff.
Yep. And the center of pressure itself can shift if the satellite's attitude changes, so it's a bit unpredictable.
Okay, so thin air can still mess with you. What about solar radiation pressure? Sunlight pushing things. Sounds tiny.
It is tiny, but relentless. Photons from the sun carry momentum, and when they hit the satellite, either absorbed or reflected, they exert a tiny pressure.
Like a super gentle breeze.
Kinda. And again, if the center of pressure for the sunlight force isn't lined up with the center of mass, you get a torque.
And over time,
Over time, especially for big light structures like satellites with huge solar panels, this tiny constant push can actually cause significant changes in attitude. It adds up.
wow. Sunlight nudging satellites around. That's pretty cool.
Hmm.
Okay, third one. Gravity gradient torque. That sounds different.
It is. It comes from gravity itself. Remember, gravity gets weaker with distance.
Sure, inverse square law and all that.
Right. So for a satellite that has some size, some length, the part closer to Earth feels a slightly stronger pull than the part farther away.
Okay, a tiny difference, but it's there.
And that tiny difference in force across the body of the satellite creates a torque. It tends to try and align the satellite's axis of minimum inertia, the one it's easiest to spin around with the direction to Earth, the local vertical.
So gravity itself tries to line the satellite up in a certain way.
Yes, like a dumbbell wanting to point end on towards the Earth. And what's really neat is that engineers can use this. It's a basis for passive stabilization.
Passive, meaning
Meaning, you can design the satellite's shape and mass distribution so that this gravity gradient torque naturally keeps it pointing roughly towards Earth without needing fuel or active control systems all the time, using physics to your advantage.
that is clever, letting gravity do the work. Okay, so we have these torques trying to mess things up. How do we fight back or use them? The book mentions spin stabilization.
Right, we touched on it with Stardust. Spin stabilization is a common technique. You intentionally spin the satellite, usually around its axis of maximum moment of inertia.
Why maximum? I thought gravity gradient used minimum.
Good point. For spin stabilization, spinning around the axis of maximum inertia provides the most stable configuration against disturbances, like a gyroscope. Remember our torque-free discussion? Pure spin about the axis with the largest inertia is inherently stable.
Ah, okay. So you give it a good spin.
You give it a good spin, which gives it significant angular momentum. This makes it act like a gyroscope. It strongly resists any external torques trying to tilt its spin axis.
Like trying to push over a fast spinning top is hard.
Exactly that principle. You might need an initial torque to get it spinning, and maybe occasional small bursts from thrusters, a control torque, to counteract the slow drift caused by those external torques we talked about. But the spin itself, provides the main stability.
So giving that spin creates this inherent resistance to being knocked off course, rotationally speaking. A good sense of balance.
Precisely. And that kind of brings us full circle, understanding the basic dynamics and how we manage them.
Okay, let's try and wrap this deep dive up. We've covered quite a bit. From just defining attitude
Why it's so critical.
to the basics of rigid body motion, angular momentum, torque.
Euler's equations, the core rules,
And then that fascinating torque-free motion, the wobbles and cones.
and the real world nudges, aerodynamic drag, solar pressure, gravity gradients.
And finally, how techniques like spin stabilization use these principles to keep satellites doing their jobs. It really underscores how vital this is for everything from communication to science missions.
Absolutely. None of it works if the satellite isn't pointing the right way.
So, thinking about all these constant tiny forces and the need for long-term stability, it really is like a constant balancing act up there. What do you think is maybe the most surprising or biggest challenge in keeping a satellite pointed correctly for, say, decades?
That's a tough one. Maybe just the accumulation of all those tiny, unpredictable disturbances over very long time scales, or perhaps modeling them accurately enough in the first place.
Yeah, makes sense. Or maybe a question for our listeners. Now that you have this picture of satellite attitude, what future missions do you imagine will need the absolute cutting edge in pointing accuracy? Like, what demands the most sophisticated control?
Ooh, good question. Maybe things like space telescopes looking for exoplanets, or laser communication systems across vast distances.
Could be. Well, if this peek into satellite dynamics sparked your interest, definitely check out Spaceflight Dynamics by Craig A. Kluever. There's way more detail in there.
For sure, it's a great resource if you want to go deeper.